Welcome back once again, dear students, to another session of econometric methods course. In today's session, we are going to discuss about the problem of heteroscedasticity in regression models. The topics to be covered in this module includes the meaning of a heteroscedasticity problem, the sources, consequences, tests and remedies of heteroscedasticity problem. Let us go to the problem. Let us see the problem of heteroscedasticity. Heteroscedasticity is a composite word consisting of two separate words, hetero and scedasticity. Hetero means different, scedasticity means variation. So, heteroscedasticity means literally different variations. The opposite of heteroscedasticity is homoscedasticity. This is also a composite word consisting of two words, homo and scedasticity. Homo means same, scedasticity means variation, that means same variation or constant variation. So, homoscedasticity means same or constant variation. Let us go back to the regression model. Let us take a regression model yi is equal to alpha plus beta x I plus ui. The prominent OLS assumption on u is expectation of ui square is equal to sigma square for every I, means variance of ui irrespective of I is constant. So, this assumption is known as homoscedasticity assumption. If the variation expectation ui square is equal to sigma I square or a variable for every I, then the situation is known as the presence of heteroscedasticity problem. This has got a consequence for the interpretation of the OLS model or regression model. Let us see the consequences of heteroscedasticity. We know that beta hat is equal to beta plus sigma wi ui. Expectation of beta hat is equal to expectation of beta plus sigma wi ui. Ui is the only stochastic variable. So, you can take the expectations only for that. So, this equation becomes beta plus sigma wi expectation of ui, and this ui is 0 because that assumption is not violated, only the assumption of homoscedasticity is violated here. So, this is equal to 0, and so this term will become 0 and the whole term will go off, and that is 0, that is beta, and so we conclude expectation of beta hat is equal to beta. Now, we may conclude beta hat would remain unbiased in the presence of heteroscedasticity. So, the presence of heteroscedasticity would not affect the property of unbiasedness of the OLS estimators. But suppose let us take the variance of ui is equal to sigma I square, that is proportional to the zi square, that is sigma I square is equal to sigma square into zi square and another variable. Consider a regression model in its deviation form. Small yi is equal to beta xi plus ui. Divide both sides by zi, we will get yi by zi is equal to beta xi by zi plus vi, where vi is equal to ui by zi. The variance of vi is equal to variance of ui by zi that is equal to 1 by Zi squared variance of ui. We know variance of ui is a variable, that is sigma square Zi squared. So, both get cancelled, that is equal to a constant. So, the variance of Vi is a constant, means Vi is a homoscedastic error. So, applying OLS we will get efficient estimator. So, beta star is an efficient estimator. If you run the OLS yi by zi on xi by zi, if that regression is if the OLS is applied on this regression, your beta star is regular estimator. So, variance of beta star is equal to sigma square divided by sigma xi zi whole square. In the presence of heteroscedasticity problem, we can derive that variance of beta hat is equal to sigma xi sigma I square divided by sigma xi square the whole square. If we substitute sigma I square is equal to sigma square zi square, we get sigma xi square into zi square sigma square divided by sigma xi square the whole square. Then we can rewrite this expression as sigma I square sigma zi square xi square divided by sigma xi square the whole square. Now, we may take the ratio between the variance of B star, that is the efficient estimator, got after dividing zi square zi both sides of the regression, and this one is the OLS estimator. So, if we divide, we will get to know the first term is the variance of beta star, and the second term inversed, you get the second term. So, variance of beta hat is inversed here. So, if you divide and we get one expression, this expression is of the form sigma ai bi the whole square divided by sigma ai square into sigma bi square, where ai is equal to xi zi and bi is equal to zi xi. Here sigma ai bi the whole square is less than sigma ai square sigma bi square. So, this is a common algebraic inequality. This expression is equal only if zi is a constant. So, naturally we can derive that from this expression. Now, we may conclude that variance of beta star is less than variance of beta hat. So, now the variance of the OLS is not the minimum variance estimator. So, now we can conclude that there is a better efficient estimator than beta hat is available, that is beta star. So, in the presence of the heteroscedasticity problem, the OLS estimators does not have the minimum variance. So, the variance of OLS estimators do not have minimum variance, and also the estimator for the variance of the standard error is biased. Sigma hat square is equal to sigma ei square by n minus k is biased. So, you have double problem. One, the application of the ordinary least square formula for the variance has got two problems. One, the OLS estimators do not have the minimum variance, and also the estimator for the stochastic error variance is biased. To explain this phenomenon, let us give one example. This is the OLS, this is the regression model with heteroscedastic stochastic error term, because UI follows a normal distribution, the zero mean, and xi whole power k variance. If this is known, let us take one example, specific example, k is equal to 2. That means sigma I square is equal to xi square. We may divide this equation by xi both sides, then we will get yi by xi is equal to alpha by xi plus beta plus ui by xi. The variance of this equation will calculate as variance of ui by xi is equal to 1 by xi square into variance of ui, that is equal to 1 by xi square, and xi square get cancelled, that is equal to 1. Now, the variance is a constant for this equation. For this equation, the error term is heteroscedastic. For this equation, the variance of this error term is 1. So, homoscedastic. Applying OLS for this equation would give generalized least square estimates. We call it GLS estimates. Standard errors may be computed for this equation. That would be a very efficient variance. A study was done by Davidson and McKinnon in 1993, and they did that study using the Monte Carlo experiment with 20,000 repeated samples. See the results table. The first column is about the value of k, different values of k is given 0.5, 1, 2.0, 3 and 4. The second set of column is the standard error computation of alpha, and the third one is the standard error of beta. In the standard error of alpha, you have got two columns, one is the OLS and the other one is GLS. OLS is the first model standard error for different values of k. So, the first column gives you the OLS standard error for different degree of heteroscedasticity. The next column GLS is giving you the standard error estimate for different degree of heteroscedasticity. We may compare the standard error estimate for beta for OLS and GLS procedures. You may see the OLS standard error is always bigger than the GLS standard errors. So, this can clearly tell you the OLS standard errors are always greater than the GLS standard errors. We have seen that in the presence of heteroscedastic error variance, the variance of the estimators of regression coefficients are always larger. It has implications for the statistical inference of them. For instance, the significance of the regression coefficients in the presence of heteroscedastic is misleading. So, we have to correct for it. Unless we correct for it, any statistical inference on the regression coefficients is very misleading. Though it will not affect the R square value and F value, the individual T coefficients will be highly misleading, and so the statistical inference framework cannot be done casually in the presence of heteroscedasticity problem. Now let us see the sources of heteroscedasticity problem. When there is a wide disparity between the largest and the smallest observed values, the heteroscedasticity is likely to occur. Larger the disparity between the higher and the lower values, the higher the likelihood of heteroscedasticity problem. Let us see some instances of heteroscedasticity problem. In consumption or saving studies, as income grows, people will have more discretionary income and hence more scope for choice about disposition of their income. Therefore, the variability in saving and spending behavior is likely to be more in the high income family than poorer families. This phenomena can be observed in the firms as well. Firms with larger profits show larger variation in dividend payouts than companies with lower profits. Secondly, in production function studies based on the sample of firms, the managerial variability increases with increase in size of the firm. And thirdly, following the error learning model, error in the behavior of the rational people tend to go down as they learn from their mistakes. The variation in production or variance sigma square is expected to decrease with the scale of production. Fourthly, as the data collection techniques improves, the error in the measurement is likely to decrease. Bigger banks with sophisticated data acquisition equipments are likely to commit fewer errors in the income statements than the smaller banks. Fifthly, heteroscedasticity may also occur due to the presence of outliers or unusual observations that are much different from the ordinary observations, that are much different, either too small or too large from the regular ones. The heteroscedasticity may also occur due to the omitted variables. Sixthly, the omitted variables may also tend to change the error term in the same direction of the included variables. Apart from that, the functional misspecification may also lead to the heteroscedasticity problem. With this, we may conclude today's session. Today's session, we saw the meaning of heteroscedasticity problem, the consequences of the heteroscedasticity problem, and also the sources of the heteroscedasticity problem. In the forthcoming session, we are going to see the tests for the heteroscedasticity problem and the remedies for the heteroscedasticity problem. So, let us see in the next session. Thank you so much.